Okay, great. So now we're on chapter 15. So chapter 15. And what we're going to study in this chapter is interacting quantum field theory in naught dimensions. Okay, so you've studied the free theory. Now we're going to start studying the theory with interactions, and you're going to really start to see how do the Feynman rules work. Okay, so what should I tell you? Well, first thing, we always specify our theory by giving an action. So we've got alpha over 2 phi squared. That was from the free term. And then we've got plus g phi to the 4. And we've already discussed why you should think about this as an interacting theory. And then what do we want to compute? Well, we want to compute these correlation functions. Phi to the n. This is an integral from minus infinity to infinity d phi e to the minus s phi to the n. Oh, and there is a normalization. So let me sneak that normalization in. That will be important. Okay, good. Okay. Some normalization n that we will have to specify. Okay. And what is the goal of this chapter? Just so that you know where we're going towards. The goal is to derive a set of Feynman rules that will allow us to compute phi to the n. So that's going to be the goal of this chapter. By the way, when we've learned how to derive the Feynman rules in naught dimensions, it's a very small step to derive the Feynman rules in 3+1 dimensions. Okay, so what do we do? Well, by now, I think that you could even guess the first thing that we're going to do. We're going to introduce z of j. Z of j is equal to some normalization times the integral from minus infinity to infinity d phi. The normalization in z of j and phi to the n are exactly the same. Then we've got e to the minus s plus j phi. What is the name of this? This is called the generating function of correlators. Okay, so that's what we're going to focus on calculating. Why is it called the generating function of correlators? How do you generate a correlator given z of j? Well, it's quite straightforward. Phi to the n is equal to dn dj to the n on z of j evaluated at j is equal to 0. So how do you generate a correlation function? Well, for the correlator phi to the n, take n derivatives of z of j with respect to j, and then set j is equal to 0. So it's because you can extract these correlators from z of j, as shown in the red box. That's why we call it a generating function of correlators. Good. Okay, so let's now calculate what z of j is equal to. Well, z of j will be equal to, we'll have the normalization, we'll have an integral from minus infinity to infinity, we will have d phi, and then we've got e to the minus s, so this is minus alpha over 2 phi squared minus g phi, and then plus j phi, g phi to the 4, sorry, and then plus j phi. So I haven't done anything, I just plugged in what the action s is. Okay. This next step is really just for clarity, but I'm sure, well, many of you would just skip it, but let me just put it in. So what I've done is I've separated out the interaction term. Now you see, what is the problem with this z of j? Well, if you look at this integral that we have to do, it is not Gaussian. It's not Gaussian because of that extra phi to the 4 that's sitting there, okay? Because it's not Gaussian in general, it's not easy to do. Now, it turns out that with a phi to the 4 sitting there, you can actually still do the integral exactly if you're smart enough. It's really not that easy. So we're instead not going to do the integral exactly, but we're going to do what we usually do in quantum field theory. So we are going to assume that G, the coupling strength, is very small. And that means it's very much less than 1. So when G is very much less than 1, we call this weak coupling. So we're going to assume that we are at weak coupling. When we're at weak coupling, we can use perturbation theory to do the computation. And what does it mean to use perturbation theory? Well, concrete, it means we will expand in G. And when we do this expansion in G, what you will see after we finish doing the expansion is that knowing the free theory is good enough to solve this theory perturbatively to any order in the coupling. Okay, so we're going to be using our known solution of the free theory to now study the interacting theory. So let's keep going. So we've got our normalization n. We've got an integral from minus infinity to infinity, d phi. Now we've got this exponential on its own. And you know how to expand an exponential. It's a sum from n is equal to 0 to infinity of minus g phi to the 4 raised to the power of n over n factorial. Then we've got e to the minus alpha over 2 phi squared plus j phi. Good. So what you can see is if g is very small, then the nth term, which is multiplied by g to the power of n, is very, very small. So for small enough g, we might only need the first few terms in this expansion to get a very good approximation. And for example, in quantum electrodynamics, the perturbative expansion of the theory is surprisingly accurate. Okay, it gives you very good agreement with experiment. The Feynman rules are a set of diagrams for carrying out this perturbative expansion. So they are very much related to perturbation theory. Okay, in the next step, while we'll keep the normalization, we keep the integral from minus infinity to infinity d phi, we'll keep the sum from n is equal to 0 to infinity. And now comes the first non-trivial thing. We've got minus g. Now, instead of writing a phi, I'm going to write a d by dj of the exponential, because every time I differentiate this exponential with respect to j, I bring down a phi. So the phi to the 4 can be replaced by d4, dj4. That replaces the phi to the 4. This is raised to the power of n factorial e to the minus alpha over 2 phi squared plus j phi. So let's just stress this. The phi to the 4 sitting here has been replaced by d4 dj4. So make sure you understand why that replacement is possible. It's just because d by dj acting on the exponential gives us a phi. So it's pretty straightforward. Now, notice that this whole piece of the expression over here, of the integrand that I've put into the blue box, nothing there depends on phi, so I can take it out of the integral. So now I've got a sum from n is equal to 0 to infinity. I've got minus g d4 dj4 raised to the power of n over n factorial, and this acts on an integral from minus infinity to infinity, d phi, e to the minus alpha over 2 phi squared plus j phi. Now, let's look at what is sitting inside this green box. Look at this factor over here. What is this equal to? Well, this is what we called this was what we called Z of J for the free theory. And we calculated it. If you remember, this was just e to the j squared over 2 alpha. So this is now using, now we are making use of the solution of the free theory. Okay, good. So what do we get? We get that Z of J is now equal to, it's a sum from n is equal to 0 to infinity of minus g d4 dj4 raised to the power of n over n factorial e to the j squared over 2 alpha. So with the help of perturbation theory and the known solution of the free theory, we've been able to calculate Z of J for the interacting theory. Good. We will continue in a moment.